Hello, everyone. Welcome to the second day of ITC. Before getting started with the keynote and visionary talks, I'd like to take this opportunity to offer a tribute to a person whose name, to me at least, is almost synonymous with ITC. And that is Don Denberg, who sadly we lost on September the 30th this year. Don has given or had given more than 40 years service to ITC as part of the program committee and steering committee, and indeed he was the longest serving member of anyone on the committees with ITC. He was immensely concerned with quality. He literally hand scrubbed the advanced and final program until they were perfect, and in conjunction with that he was the official grammarian and made sure that grammar was correct, corrected mistakes in paper titles and abstracts, was absolutely a perfectionist in terms of grammar. He was also, for a very long time, the official photographer, took many pictures of ITC events and served as an excellent photographer and continued his interest in photography in his private life as well. He was intimately familiar with all the bylaws, the IEEE, and he also helped assure that ITC was run correctly. So Don, his memory will live on. And with that, I'd like to pass it over to Teresa to continue with the session. Thanks.
Well, good morning, everyone. I first want to just say that we have started this ITC exhibition giveaway. So we're giving away 2 iPads per day for the next 2 days. You have to be a registered full conference attendee. You have to visit 4 or more exhibition companies, not just 4 booths, during a single day. And you need to provide your email and name to the host of the exhibition company as evidence. So when you join the Q&A, you have an opportunity to put your email and your name. The drawing will occur at the end of ITC, and winners will be posted at the ITC website and contacted directly. All right, so everyone, good luck. All right. So I just want to let you know that if there's time after the keynote, we'll allow a couple of questions. So if you have any questions, put them in the Q&A window. Our keynote speaker today is Ritu Favre. She's Senior Vice President and General Manager of the NI Semiconductors business and has been responsible for driving business growth and defining the products, services, and capabilities required to meet the unique needs of NI Semiconductor customers. She's a seasoned high-tech industry leader with experience across general management and executive leadership roles in the RF and fingerprint sensing industries. Most recently, she served as CEO of Next Biometrics and was on the Cohu board of directors. Prior to her role at Next, she helped build profitable businesses while holding senior management positions with market leaders such as Motorola, Freescale Semiconductor, and Synaptics. She has recently joined the board of Valmont Industries. Ritu is a member of the Global Semiconductor Association Women's Leadership Council, which is aimed at inspiring and sponsoring the next generation of female leaders in the semiconductor industry. She's also on the advisory board of Microfacturing Institutes, which aims to reskill Americans to contribute in the tech industry while increasing diversity. She received both her bachelor's and master's degrees in electrical engineering from Arizona State University. The title of her talk is Applying Digital Transformation Technologies to Semiconductor Product Development. And with that, I'm extremely excited to welcome Ritu Favre.
Thank you so much, Teresa. Thank you very much for having me today at the International Test Conference. I've been in the semiconductor chip making industry, as Teresa mentioned, for over 30 years, and I'm really excited to speak with you today about the advances that we're seeing in the industry, specifically around applying digital transformation technologies to the semiconductor chip making product development flow. It goes without saying that the pace of technical innovation, development, and adoption continues to accelerate. It should come as no surprise that new technologies will disrupt industries and the approaches to test and measurement. However, one thing that has changed is the rate of new technology development. This is happening more quickly than ever. We see more global competition and an acceleration in semiconductor chip makers' time to revenue requirements. I will not go into all of the examples on the slide, but I do want to zoom in specifically on 6G. Yes, you heard that correctly, 6G. Many of us know that the cellular industry has begun to deploy 5G networks and phones around the world. We're in the early phases of 5G millimeter wave deployments today, with this technology available in limited portions of select geographies. Yet, even as 5G is just beginning to roll out, researchers and innovators are already in brainstorming mode on 6G. Ultimately, many of the use cases and technologies that are being dreamed up right now will create new technical requirements for semiconductor products in the not so distant future. Of course, being first to market with a successful product requires careful attention to quality and reliability. Even some of the most respected companies in our industry have had to manage through field quality and reliability issues. For example, many of us might remember the Galaxy Note 7 and MacBook Pro issues, both of which faced thermal problems severe enough to force bans from the FAA and cause massive recalls. These examples underscore the inherent tension between getting to market first, as well as testing every imaginable corner case of a product's design and ongoing operation. Semiconductor companies are squeezed between these competing interests, and it drives economic, technological, and even organizational challenges. All right, so, oh yeah, I think I got through. Enterprise software tools combined with more classic test and measurement hardware can provide this capability. By collecting and comparing product end-use data to data collected during product development, engineering organizations will be able to more strategically decide what to test at each stage of the product development flow, enabling them to eliminate redundant testing or to expand test coverage in areas prone to field failure. To recap, the challenge between getting to market first and getting to market with quality product creates tension for modern engineers in semiconductor product development, and especially test and operations floor managers. Some of the economic and technical challenges of this pace are more obvious. There is a race to deliver competitive products to market as quickly as possible to catch the next phone cycle or the next new server or data center node. The first few companies that can hit these market windows will enjoy a better competitive position in these new technology inflections. The one area that people may not realize can be challenging is the organizational structure in semiconductor chip companies. Design teams, validation teams, and production teams are dispersed across the globe and heavily matrixed, creating common IP, platforms, and standardization can be a challenge in large multinational semiconductor companies. In order to accelerate new products to market, efficiency in the way work is accomplished needs to be implemented. On the surface, it's easy to understand how industry best practices like IP reuse or test software standardization, for example, might drive organizational efficiency. However, implementing these best practices often requires role specialization. As a result, we continue to see semiconductor companies reorganizing their workforce to improve product development efficiency. In many ways, the design, validation, and test engineering organizations are stuck in the middle as their companies must balance cost and complexity with faster time to revenue requirements. We have seen a trend with semiconductor companies that radically reducing the time to design a semiconductor chip, taking it through validation, and then releasing the product into high volume manufacturing is a key imperative for their organization. In fact, organizations are effectively asking test engineers to release more complicated devices at a lower cost and in less time than ever before. Perhaps one of the best examples of this phenomenon is the 5G wireless standard, where device complexity is exploding. As we've been discussing, we are seeing semiconductor product complexity radically increasing. The transition from the 4G cellular standard to the 5G cellular standard is perhaps one of the most obvious examples of increasing device complexity in semiconductor chips. If we look at 4G semiconductor device, the number of test cases was determined by the number of bands and carrier combinations, while also influenced by the number of waveform and modulation types. When we progress to 5G, the number of test cases increases by another 10x. For a design, validation, or test engineer facing this challenge, merely applying the same test techniques would result in a 10x increase in test time. Thus, 5G illustrates a clear requirement for engineers to constantly innovate their development practices in order to shorten their time to revenue. In addition to modern end devices like cell phones and base stations requiring more complicated measurements, semiconductor chips themselves are becoming more complex as well. When I first got into the RF industry over 20 years ago, almost every block of a radio was a chip. Today, chip makers are combining everything from the digital interface to portions of the RF front end onto a single chip. One of my favorite examples is the radio verse product line from Analog Devices. Many of the devices, like the one that you see on the slide, are getting integrated into 4G and 5G base stations. You can see from this block diagram that a single chip contains 4 transmit and 4 receive paths, and includes onboard power management, local oscillators, and a JESD serial interface. Of course, RF radios are just one example of a higher integration that we're seeing in the semiconductor industry. You could easily pick an example from MCUs with integrated Bluetooth radios, or modern MEMS devices which integrate both sensor and processor cores into a single chip. It should also come as no surprise that the measurements themselves are becoming more challenging. For 5G millimeter wave devices, for example, the adoption of antenna in package technology means that there's no longer a physical connection to access the millimeter wave signal. As a result, many 5G millimeter wave devices require over-the-air testing. In a typical beam pattern test configuration in the lab environment, the device is placed on a 3D gimbal in an anechoic chamber, and the receive antenna measures power and modulation quality at a range of angles. Another challenging example we're seeing today in modern optoelectronics products are VCSELs, or vertical cavity surface emitting lasers, which are increasingly being used in 3D sensing applications. In fact, arrays of VCSELs enable facial recognition features on smartphones. Here, the desire to limit heat dissipation at higher peak powers is driving innovations in VCSEL technology to only turn on the laser for extremely short pulses. Although this has obvious benefits for consumers in the form of more accurate 3D sensing and lower power consumption and battery drain, it is simultaneously driving test and measurement hardware and new measurement methodologies. Finally, the acceleration of the MEMS market is sourcing a myriad of test and measurement innovations. Some of the most interesting MEMS measurements are for inertial sensing devices, because testing these devices requires physical movement of the device under test in parallel with the measurement of electrical signals. The product that you see on your screen is actually a personal ultrasound device from a company called Butterfly Networks. They have been able to use MEMS technology to develop a fully functioning ultrasound device for less than $2,000. So what does all of this have to do with digital transformation? Many of us think about the digital transformation as consumers. For example, we enjoy the benefits of using cloud data storage for photos on our mobile phones. Or we might think about the digital transformation in the way that it is driving the development of new semiconductor technologies. We all know that the world is becoming a more connected and networked world. We see that new sensing technologies capture more and more physical signals and convert them into the digital domain. This allows more and more data to be captured and fed into the network so that artificial intelligence, or AI, and machine learning, or ML, can be applied. This in turn allows for automated and adaptive control of many technologies that we use as consumers, such as our Ring doorbell, our Alexa device, or our Netflix movie browser. The same digital transformation is also driving new technologies that can be applied to test and measurement systems. For example, advances in artificial intelligence and machine learning will have an impact on the way that we produce, consume, and analyze test data. To best understand how data analytics can accelerate product development, we have to understand how test data is collected and used across the semiconductor product development flow. Starting in simulation and modeling, EDA tools produce some of the first simulation and test bench data to describe device behavior. Similarly, the test equipment captures test data in device characterization and validation, and then on into the production test phases. The comparison and correlation of the test data captured during the different phases of the semiconductor product development lifecycle can slow product release to production. The same device is carried across this flow. The design simulation data needs to be compared to the characterization data. The characterization data then needs to be compared against production test data. To guarantee that each device is performing as designed in high volume manufacturing, guard bands need to be applied at validation and in production. This can lead to lost time across the flow, as well as loss of yielded good devices. Digital transformation technologies like AI and ML present a possible solution to this challenge by accelerating the correlation across the entire semiconductor product development flow. We're seeing a trend that many semiconductor companies are modernizing their approach to product validation and characterization. Some of the best practices include standardizing on a common set of hardware and software through the stages of the product development flow to ensure that engineers are more efficient and productive. Other best practices include investing in software infrastructure so that engineers spend more time and energy understanding test results instead of writing test programs. One of the most fundamental improvements in the modern lab is the use of automation. When I first started in the semiconductor industry, validation and characterization lab test benches looked very much like the picture on the left. There were lots of instruments everywhere, and the test engineer was required to cobble these instruments together in order to test a new device. Over the past 30 years, we have seen leading semiconductor companies take a different approach to their validation and characterization labs. Instead of manually configuring each test with knobs and buttons on the instrument, these engineers are using software to automate test systems. These setups often look like a production test system than a traditional lab bench. The benefit of this automation is faster characterization times and the ability to get to production, and more importantly, to market more quickly. Our customers often tell us that they can characterize new devices coming off the assembly line anywhere from 5x to 10x faster simply by automating their lab setups. The benefit of modernizing the lab is that it allows companies to more readily produce test data that can be compared with both upstream and downstream data sets. New solutions can ingest, compare, and report on data starting from the EDA environment and through to the production test environment. Using these tools, engineers can be more ready to identify inconsistencies in product behavior from one phase of product development to the next. Enterprise data software is just one example of a broader vision to accelerate semiconductor product development through the use of software. Companies are beginning to use artificial intelligence and machine learning technologies to apply to data analytics tools to enable time to market advantages for chip makers. Test data becoming portable and following a device through the product development flow will enable predictive test methodologies, increased production testing yield, and it results in an improved time to market. Long term, the pace and speed of semiconductor product development can be enhanced by enabling engineers to seamlessly transition from one phase of product development to the next. I do hope this talk has provided some perspective on the growing role of test in accelerating time to revenue, higher quality and yield, and a reduced field failure rate. Thank you very much again for having me at ITC, and I wish you the best conference. So
Thanks a lot.
I don't know if there are some questions.
I've not seen any questions come through. So I'll just ask you a question that, as you know, I attended your 5G panel. And one of the panelists mentioned that there were riots or people protesting 5G. Do you know anything about that?
Okay, sorry, I'm really sorry. I have not used this this application before. Yeah, so I think some of the riots, if I can understand, were caused by this notion that 5G was causing coronavirus. And
Oh,
so I think
coronavirus.
that's part of what was I think that's part of what was causing the riots.
Oh, okay.
I do think that 5G will really enable a lot of new applications with the lower latency, the higher bandwidth, the higher data rates. I think there are a lot of new applications and new, just new technology that will be enabled, particularly machine-to-machine interaction, kind of industry automation, and then of course just people being able to access much higher bandwidth on their phones and their devices.
Yeah, yes, I think going forward with automotive, if we really get to autonomous driving, we have to have it
That's right.
in other areas.
That's
I
right.
don't.
As I was saying as well, 6G is just beginning to be formed, and I think that will help advance the industry yet again in a even more kind of unimaginable way, I believe.
Yeah, that's quite amazing in itself. It's already. Okay, well, thank you so much. I'm so happy that you came and gave Keynote at ITC. I really appreciate it.
Thank you. Great to do it. Thanks, Teresa. I appreciate it.
Bye-bye, Ritu.